So we're ready to start chapter 13, which is on vector valued functions. And basically 13.1 will describe what that means. So 13.1 is on curves in space and tangent lines. So first, let's define and remember like what a parametric equation is. So you would have seen parametric equations at least in two dimensions, and you define basically an ordered pair. X is f of t and y is g of t. And you can trace out functions. You would have seen this like in trig, where you had, cosine t, sine t, and then t would vary, and it would create a circle at your coordinates x, y. So you would have seen something like that. We're putting in a third dimension. We're putting in h. So the critical aspect here, f, g, and h are continuous functions of t. Okay, so that's what gives you the continuity. And so what you're doing then is you're mapping the t values, which is like a real number line. So these values over here are t, that's in the reals, are 1. And then you could start at 0, you can start at 0, it doesn't matter really where t is. Sometimes it's referred to as time, and so you can start at 0 and go forward, but it doesn't really matter. It doesn't have to be time. And then that maps to a 3-dimension curve over here. So you could have some function, come like a helix sort of thing, go like this, go in the back, and then curve up or do whatever like that. And the way we're going to define this, so that's like your curve. Like maybe when t is equal to, say -1, maybe that's -1. You could start here, and then the next t value would be here, and you would keep going. So what we're going to define, so picture essentially a point on this curve as an ordered triple, f of t, g of t, h of t. And that's some value of t, say here. And then as t varies, that is being traced out like this. Okay, so it can create whatever. It can create a circle. It can create like a helix. It could create just whatever, spirals. But what we're going to do is not just look at it like that as a point. What we're going to do is define what's called a vector valued function. So here's the definition of a vector valued function. So vector valued functions, basically what it does is allows us to use everything we just talked about in chapter 12 that had to do with vectors. So let me show you what I mean. So the definition looks like this. We use r often. R of t, and it's a vector like that, is equal to f of ti plus g of tj plus h of tk. You can also write it in the component form, which would just be the f of t, g of t, and h of t. And then we want to say where f, g, and h are continuous functions of t, and t is in the reals. So it's a real number, but it's usually they define it like on some sort of interval, a to b, and that kind of thing. Okay, so what is happening then for your function, and I'm going to use my little thing on the side here. So what's happening then is the R of t creates a vector. So this would be like a vector R of, say, -1. That vector would be an R of whatever, 0. That vector could be R of 1. And then it basically traces it out. So this is like R of, say, -1. And then this next one here might be R of 0. And then this is like R of 4, whatever. So the tip of the arrow, essentially you can see it's like tracing out the curve like that. Okay, so that's what we're going to use now for these vectors. And it creates that curve. We're going to be able to use that to do our definitions. Okay, so let's move on to the next thing. So now we want to talk about some examples. So here's an example. And since they are functions, we can talk about domain and continuity and things like that. So here's one example. So find the domain of R of t equal to ln ti plus the square root of 1 minus tj plus k. So basically, you look at the domain of each of the functions. You look at each of those domains. So first, we'll look at f of t equal to ln t. And we know that the domain of that, t, has to be greater than 0. Then we look at g of t equal to the square root of 1 minus t. And we know that inside the radical, 1 minus t must be greater than or equal to 0. And then we would basically solve this one. This is 1 is greater than or equal to t, or you would say t is less than or equal to 1. And so what we're going to use is really the intersection. Let me do a little Venn diagram over here between the two. Okay, so the domain will be the intersection of those functions, f, g, and h. So it's all of this. This is the intersections, everything in between. So if this is A and this is B, then you take the A intersect B of those functions. And then you can check that out like on a number line as well. So you could just you could graph it like this. This is all old algebra stuff. You can be at 0 and go to 1. Oops. And go to 1. Okay. And then the top one, you have t greater than 0, so it would be like a circle. And it goes this direction. And then the other one would be closed, and it goes this direction. And so the overlapping, of course, is the intersection. So the domain D would be not including 0 to 1. Okay, so domain stuff, it comes up. We have to be aware of it and all that kind of good stuff. Okay, let's do a sketch. The next example, let's sketch this. So sketch the curve given by r of t equal to cosine ti plus sine tj plus tk. And we'll say t is greater than or equal to 0. Oh, and I almost forgot back here, your f, g, your h, I didn't even talk about, but your h of t is just 1. So that's, all reals. So there's nothing to talk about for that one. But you did have a function there. It was just 1, so nothing to really do. Constant function. Okay. No idea what that curve is. I just kind of wanted to talk about natural logs and radicals and stuff. So, all right. So this next one, to sketch this, let's take a look at this. Oops, too far. Okay. So let's take a look at this function and do a little background on this one. So what we have is if you say like this is your x and this is your y, those are your variables. So basically you have x of t equal to cosine t, y of t equal to sine t. So what does that look like? Question mark. So if you eliminate the parameter, you can do so by looking at x squared plus y squared equal to a squared. So what you get, and you might recognize that. I mean, basically, I'm just kind of going through stuff you may have seen. So that's going to create what? Like if you do cosine squared plus sine squared, that is, excuse me, that is Pythagorean identity, so that's just 1. So what you get then for this is a circle, right? So you get a circle, and that's just your, okay, actually made a circle, that's good. And so you start here, and then you can plug in values too. So this is just in the xy plane. If you put in t equal to 0, then you get 1, 0, right? Cosine, so it's cosine sine, right? And then if you put in t equal to pi halves, you get 0, 1, etc. And then you go all the way around. This is negative 1, 0, and 0, negative 1. So we know it's being traced out like that then. Like it's going like this. So this is kind of the parametric equation stuff we would have seen, important case. And it traces out and goes around and around and around like that. So what's happening then for t, right? So for t, what is happening? And picture that's your z-axis, right? That's z. So as t starts to increase, it's at 0, right? And then it starts to increase. So you basically have this circle going on. But as you start going around, picture t coming up around. So what's that creating? So basically you have a circle, but what's happening then is your z value is going higher and higher as you go around that circle. So do you picture that? It's creating a helix like that. Okay, so let me show you then that picture. And I'm not going to get into it being, I'm not going to go through every little point. I just want to give you an idea what this looks like. So let's take a look at this helix. when t is 0, you're at 1, 0, 0. So you're going to start down here, basically. And then over here, it'll be a little higher, but that'll be 0, 1 pi halves. So it's basically being traced out like this, and then it starts to climb up. Right, so there's a gap right there off the z-axis, and then it continues around. And I'm just going to do a little sketch here like this. And you can go in the back, and it's going to continue to climb. So look at the book too. It has this picture. So basically, we call that a helix. Helix, double helix, that kind of stuff. So that's what happens for that function. Okay, let's continue on to limits and continuity. So limits and continuity. All right. So let's define that, a limit. So here's the definition. So let's first let r of t equal the same thing we had before. F of ti plus g of tj plus h of tk. And I'll skip some of the details. F, G, and H are continuous, usually. They can be continuous. Actually, they don't have to be. They can be continuous on a specified domain, because some places they may not be continuous. Okay, so let's look at the limit. All you got to do, the limit's actually very easy. So then, if you take, again, this is a definition, so you just do the same thing as this what it says. So the limit of r of t as t approaches a is basically just equal to the limit of each one of those functions. So it's equal to the limit of f of t as t approaches a, I. And then you just go down the line, plus the limit of g of t as t approaches a, k, plus the limit of h of t as t approaches a, k. Okay, so that's what the limit is, provided each limit exists. Okay, so let's take a look at an example. So for example, find the limit of r of t as t approaches 0, where r of t is equal to, I'll do it in this notation this time, e to the t sine t over t, and e to the negative t. So what would that be? So if you take that limit of r of t as t approaches 0, what does that equal? And notice it equals still a vector, right? When you take this limit, you still get a vector out of it. So you don't like combine them or add them together. You get basically one of those vectors on there. So when you do that limit, what happens to, so as t approaches 0, this goes to what? So yeah, that goes to 0. No, I'm sorry, that goes to 1. Try that again. That goes to 1, right? So you have your graph. Actually, I actually did graph e to the t in e to the negative t over here. So let's do that too. So you have, that's e to the t, e to the negative t. And they go through 0, 1, both of those. So those both go to 1. So what about sine t over t? Who remembers what that is? What's this limit as t approaches 0? That limit is also 1. That goes way back, but that's that special limit you should know. Nowadays, you can just do L'Hopital's rule on that, and you get cosine t over 1, and limit of sine goes, or cosine goes to 1. So it's really easy. Without L'Hopital's rule, it's actually quite a difficult limit to prove. Okay, so that's how you do limits. Just take the limit of each term. Next, let's do continuity. Okay, so continuity, remember, basically you're in 2 dimensions or even 3. I mean, you had this idea. Oops, didn't mean it to do that. You had this idea, curve. So you have a curve, you can have a cusp, but it's still continuous. You could have a corner like that and still continuous. So as I drew that from here, and then just say it approaches infinity. So on that, whatever interval that is, that's still continuous. We do have issues with the derivative on those, the cusp and the corner, but that's continuous. So in Calc 1, we define that. And if you recall, basically it has to do with the limit of f of x as x approaches a equals f of a. So the limit value must equal the function value. And that's what we often say. We say the limit value must equal the function value. And then the way it's defined basically is that the limit exists, meaning the limit equals L, and it's in the reals. F of A is defined, meaning it exists, and then they say the limit equals F of A. So basically, if you can just show that, and that F of A is real, then that's all you really need. So our definition is really virtually the same. So definition continuity. So R of t is continuous at A if 1 R of t exists as t approaches A. 2, I'll actually write it as 2, R of A exists, or I'll just say in the reals, and it's kind of this is what we mean by it being the existence of it, that it's in or in whatever dimension. Right now we're in R3. I'll just stay in R3. So it's a vector at a point in R3, and then 3 is the same as I have above, essentially. And really, 3 is the key to everything, in that the limit of R of t as t approaches A equals R of A. And that is in whatever dimension you're in. So I'll just make this a for example kind of thing. So just like in Calc 1 stuff, single variable, we have different cases. We can have a function that does this to a point and then jumps. That's not continuous. You could have a hole in the graph. That's not continuous. You could have a vertical asymptote. Right? So these are not, this doesn't exist, not continuous. Yeah, this would be, sometimes they call this a jump discontinuity. It's just a discontinuity. This one is often referred to as a removable discontinuity because it's just one point. And then, of course, this is an infinite discontinuity because they approach infinity. So you can't get rid of it. It's like dividing by 0. Okay. Let's look at a couple examples here. All right, so next example says this: determine values of t for which r of t, which equals cosine ti plus the square root of t minus 4j plus ln t k is continuous. So basically you want to look at the domain of each of those, and it's because they're continuous on their domain. So let's take a look at that. So the first one, we'll look at each one of those. So the first one, cosine t, is continuous on R. Second one, t minus 4 has to be greater than or equal to 0. So t has to be greater than or equal to 0. And the last one, we know t has to be greater than 0. I said 0, I meant 4 there. So that's a 4. So R of t would be continuous on what? What's the intersection between all of those? So therefore, R of t is continuous for t greater than or equal to 4. Okay. Let's see where we're at. It's a good time to stop the video before we move on. We'll do 2 videos for 13.1.